story with primes is there are things involves prime numbers. That are like the processes that only works one way. And coming back is difficult. So mathematical processes that you can only go one way and it's coming back is difficult are very valuable things to write ciphers, to write, to design secure systems. So the most well-known one-way process is to multiply two primes. It's very simple. Given two primes, you can multiply them. So given two primes, P and Q, we can find P times Q. We multiply them using a multiplication, a computer or something. But given n, it is very hard to find P and Q. I'm not talking about, of course, 17 and 23. Even that, you can sort of find it difficult. But talk about numbers are like 150, 200 digits long. Two prime numbers, you multiply them. And then it's very hard to find this. Actually, you can design primes. You can find big primes that when you multiply them, to factor them back out, today's the biggest, fastest, best computers takes more than the age of the universe, galaxy. I mean, we are talking about big times. Okay, so it's not it will take time, but it's impossible. So because today's computers, you cannot do that in any of our lifetime. That means they cannot say break the code that you write using some prime number, some ideas involving this process. So suppose that you use this one-way mathematical machine to write a secret code. That means people cannot solve it. You cannot break this code in lifetime. That means it's secure. Nobody can break your cipher. So prime numbers are good to design one-way mathematical machines. So this is used to design one-way mathematical machines. So how do you, like, let's go back to about this security business. So suppose you're like two parties involved. This could be like your son and daughter. They want to sort of secretly pass some information between each other. Of course, it could be you and your server that you send your password to go into the... It could be where your emails are. This is you at home. It could be your phone. It could be anything, right? Suppose you have two parties which wants to communicate with each other. Now what you do, I mean, if these are kids, they will secretly give this to each other. But nowadays, all this information is open. open to public. Everyone can interfere and look at this. So it's open. I mean, people can break in and read what you're sending. You can say, I'm going to make a cipher, like write something in a secret code. Change all the numbers to something else and send it. But if you do that, how B will know that? How the other person will know that you did this? So some way you have to pass that information to B, right, at the beginning, somewhere. You have to say, I'm using this technique of, say, I'm using numbers for letters. I'm using these numbers to make it more interesting, say. And my letter will look like all the numbers, but I'm using this. But you have to pass that information too. Some point, somewhere. In the past, people passed this information secretly, like in the World War times, whereas all this air communication with the planes, they had special ciphers that they had to carry with it themselves, and anytime it's being code, people can understand what the communication is. There's all these movies about this, right, Enigma, and so on. So it's an important thing to write things in code, but then you have to tell that what you're doing to the other person. But nowadays, that even is open. It's open to that it can be interfered, so people can see it. So under the assumption that everything can be seen, how you send any information to other person, how you secretly communicate between A and B. This is how you do it. This is, I'll explain this in terms of boxes. Now we'll change the boxes into prime numbers and so on. This is what you do. You go to a grocery store and buy a lock. Okay? So this is your lock. And you tell the person, B, do the same. They have a key too, opening the lock. So the key A opens it. You have a box to communicate. So you buy a box, you buy a lock, you lock it with the A. You lock it, and you send it, and the postal service, whatever, to B. On the way, people look at it and say, oh, there's a lock on it. I can't open it. And the only person who can open it is A. It comes to B, and B, of course, can't open it. It's locked. It's locked by lock A. So instead of trying to open it, what B does is puts his lock on the same place, locks it with B. So now there are two locks on the same box. Okay? And then it sends it back. A receives this box with two locks on it. So there's A and B on it. But A has the key for the lock A. So it opens the lock A and takes his lock away. Now there is only one lock, which is lock B. So it sends it back to here. Sends back to B. Now B receives this box with only one lock, which is B. But B has the key for it. So he opens the lock, opens the box, and gets the information. Every communication was open to public, but they couldn't see it. I mean, they couldn't open these boxes, right? So you pass this information with your own ciphering method without telling what your ciphering method is to other person. This is the basic idea of how your cell phones work, and how every communication uses this idea, that you do something and the other person does something on it, and then you go back and forth. Let's do this with numbers. So you want to pass some information. You make the information to a number. It could be 0, 1 sequence too. Suppose you made a number, big number, from your information. You are A. This is B. You want to pass this information to the other person. Now, your lock is P, a prime number. Your key is that too. Lock and key both, a prime number. You choose a prime number, a possibly big one. The bigger it is, the better it is. You pick a prime number. B also picks a prime number. Q, a prime number. Again, a big one. So A does this. A sends N by multiplying it with P. We said how difficult it is to see the primes inside a big number. So it's impossible in today's computers to find P in it. It's such a big number, you can't find P in it. B receives this.
But can't they find the components of A and easily?
Components of what?
Is N a prime number? No.
N is some number. But that's also, you can choose a big number there too.
But if it's not a large prime number, it can be easily deciphered.
You choose a big number. You can sort of add ones at the end. It doesn't have to be a prime number either. It's some number. But the idea is you can always make this so that P is hidden in there. You can't find it unless you know the P. So you can't find P in it. It's like the locked.
If we find the components of N, then we just reach the information, but not whole information. Right?
So all the information is in the number N. So if you know the number N, you know the information.
So
But
so we need to find P.
If you know the P, you can always find N out of this number. Yes, you're right. But only A knows the P. Basically, it is your lock that only key is P. Okay. So the key is P, and this is a locked box. Only people who knows P can find N. N is the information inside the box. Now, B receives NP, but again, like everyone else, he can't see the P in it. It's big. So what P does, sends it back, but not like that, by multiplying it with Q. So made it even bigger. Anyone who sees these numbers, who sees NP or NPQ, have no clue what N is. They can't see it inside the number. So big.
Why do they multiply it? They can simply add.
They can do what?
They can add the numbers.
Add the numbers.
It will increase the amount of information. So it won't.
There's actually other methods, like you can take powers and so on. This is the most simple one.
I mean, it increases the digits so much.
Huh?
It increases the digits.
Yeah. But we multiply. Say, this is one process. When we multiply, you can't see P or Q, right? So everyone agrees that it will still be hidden, right? N is still hidden in there. Now, A receives this number. The difference between other people and A has P. So what A does is divide by P and then finds this number. Nobody else can do it, but A can do it. This is basic to opening your own lock. A still cannot see the number n. It's still hidden there, but can send it. So again, on the process, somewhere interfering only sees NQ, cannot see N again. But B received NQ, can divide by Q, and get N. Because B knows Q. So N started here and end up with here. And nobody else in the, like seeing these numbers, were able to see N.
Does they know what is NP is?
What is?
What NP is?
NP is. B knows it, but it can't see the N in it because B doesn't know P.
What about A?
A knows N. Of course, because they know P, they know NP. They know NPQ.
Then A can reach what?
Yeah, Q. But we are trying to pass this information this way. So yeah, you can use this to get the Q as well. But this way communication is what we're trying to pass this here to here. Yeah? I mean, as long as you can pass one string of numbers, then everything else you do, you can use that string of numbers to code, to cipher your communication. So the difficulty is passing at least one string of numbers without getting seen. So this is how it is done. Actually, it is done also, I mean, this is one, but it's also done this way. Let me say, we had a faculty last year, he left, but he told me that this is actually what's going on. So you choose a big prime number, P, a prime number. You publicly announce it. Everyone sees it. So you publicly announce this is the prime number we're going to use. And then you have information that A, this time information is A. You want to pass that information to here. And you can send it directly, right? So this is what you do. You choose a number n, and B chooses a number m. Again, A knows n, B knows m. So what you send, not A, but A to the B, A to the n, modulo P. Modulo P is the number you get after you divide by P, the remainder of the P division. Again, P is public. Everyone sees P. But they can't see A when they only see A to the power n. So apparently another difficult one-way mathematical operation is taking powers. You can take a power of any number in modulo some prime, but you cannot see the root. You can't take nth roots in the same efficiency. So this is actually much more complicated than just barely multiplying. Apparently it's much more hard to solve equations an to the b modulo p and find a. So because of that, the secret communication uses exponents, taking powers. So you take a, you raise it to the n power and send it. Again, nobody can see a. They can only see a to the n. Only person who can see a is the one who knows n. Okay? And only a can see a. And b cannot see it either. But what b does, b sends it to its n power. So it takes a power over again. And again, this in the interference, people see this number. But it's a very big number. You can't find a in it. It's hidden. Uh-huh.
If you are able to interfere in both times,
Uh-huh.
you know the.
Still, you may not be able to find A, even though you know both of them.
In this case, you know Q.
In this case, you can find Q, but you can't find P out of this.
In the third time you can find them.
Yeah, I guess this doesn't work because third time is the best.
This one is the.
Yeah, maybe that's.
Asymmetric.
Yeah, maybe this is only. Yeah, this one is a problem, right? You can find Q, you can find P. Maybe that's why they use that.
In this case, we are also.
In this case, I don't think all-knowing tree does.
When if we look at A to the n, and if we know A to the m times n, we can say what m is.
No, I don't think you can. Finding the powers is not possible. Just know, because you know the root.
For instance, we have A to the n is 7. And
So,
to the next, then n is 2.
maybe that's something called asymmetric. Maybe it's only one way they can interfere, but not the other way, or some. So this method obviously doesn't work if you know all three methods. But maybe you just need to know two, and then third one you can't see it. Okay. So
It's just the basic idea behind it.
I mean, yeah, that's the idea, I guess. So you take the nth root by knowing n and pass it to here, and then you take the nth root and you find a. So the process of taking nth roots and finding a, and the process of taking nth roots on this and finding am, you can do, but yeah, you interfere a to the n, a to the m, and a to the m. I'm not sure you can get a knowing all this. But here, there is, so somebody interfering all three will be in good shape to know n. So here, you should only allow interference in one direction, not both directions. At the end, this is called building locks using mathematics. So you can build locks by a process like taking power mode P, where you can't find the roots, or you can build locks by multiplying two numbers. But you have to build them in such a way that I guess all three interference should not give you the number n. Here, I think this is something that we haven't covered, so maybe we shouldn't discuss this one this much. But this is what is used, that the power. You actually work with some even big powers of P. Yeah, this one I should have been careful, I guess. I guess you can only allow interference one way, maybe. So,
And what's the importance of multiplying with a prime number? Any arbitrarily large number would be the same.
So if you take a number, multiply with a prime number, you get a big number, and that number you cannot factor out. If it is so big that you cannot find the prime in it.
Even if we factor out, we don't know the amount.
If you can find the factors, then you know n. You know the prime. The idea is that it's so big that you can't find what prime sitting in there.
If it is not prime, when you start to trying finding the prime numbers in it, each time you find the prime number, your process is getting much easier to find the number. The total number.
You're under
the prime number. the progress will continue and continue and
Yeah. I mean, you check the first smallest prime, say it's divisible by 2. It's not, so you check the next prime. You check the next prime. So each time you check the primes, you have to also know all the primes. You only know primes up to a certain level, right? So you cannot check.
In the end, n is not a prime number, so I can factor out the factors of n. And
But
I will be left with,
if you knew the n, but nobody knows the n except a.
but I have a multiplication of n and p. So,
But
for
no.
example, if n is divisible by 2, then n times p is divisible by 2
Uh-huh.
as well. So I can divide by 2 and continue on. So in the end, maybe
But
after
they're not divisible by 2. So.
if it has
Uh-huh.
and can be a multiplication of 14 prime numbers.
Uh-huh.
And if I divide n times p by these 14 numbers, which can be very small numbers,
I mean, what I'm saying, I can find 2 big primes and multiply them to each other. And this person cannot find p and q.
but n is not a prime number. So
Just forget about that. Just 2 prime numbers, they cannot find p and q. So I can choose n as one of the primes as well if you want. So I can choose a prime here if that's what worries you.
but then how can we encode the information?
I can use a number which is like 100 something digits using that. Nobody knows that prime except you. You choose it. Choose a very big prime. It's a big C. It's like a needle in a haystack. Nobody knows this, which prime you choose. So you can use that as decipher your thing. Is it clear now? Or? I mean, you're thinking this like a number, like a small thing. Like it's not. It's a big number again, and it can be taken as a big prime too, if you want.
I'm sending in information, so why would my information be a prime number?
Your information is coded using this prime number r.
So when I'm trying to send another information which is
Uh-huh.
different from r, which prime number I'm going to use?
You don't have to. This is just say a string of numbers that you can always use it to cipher everything you send after that. For example, you want to send something, a string of numbers. Take this number, multiply with 100, and add that onto every digit. That will already create a very complicated thing. And then you want to send another number, do the same thing for that number. So anytime you want to send a number, take that number, multiply this r with, say, 100, and add it. People who doesn't know r will not be able to see it. And this, do it with same thing with A2. Doesn't matter. Like you can use it for different purposes. You're not going to use it the same way. But you will have a hidden thing that nobody sees except you and B now, because B got that information. That's. I mean, this is an introduction to different techniques, right? So if you want to read more about these, there are sections in the book, and there are also more information. What I will say here is the analogy with boxes, with locks, is exactly how it is done. So it's always done in this way. And the question is how you design these locks in a mathematical environment, how you design them for your communication changes from country to country, right? I mean, sometimes one country uses a different method to communicate, and then another country doesn't know it. So you could design these mathematical locks in different way. It doesn't have to be the same way. But communication is done using this: put a lock, send it, put a lock, send it, open your lock, send it, open your lock. That's how it is done. And one of the ways to do mathematical lock is use prime numbers to take powers of numbers, mod some powers of p, or in a naive way, use multiplication. But with multiplication, I guess it has to be one way, which I don't. Okay. Any questions? Anything else you want to? There is this common joke in the US that people who works on prime numbers, mathematicians who work in prime numbers, as soon as they find something very valuable, they disappear. They're suddenly the next day, they are not there. Their kids are not there. Nobody can see them anymore. They've been moved by national security to somewhere else secretly, because they discover something about prime numbers. So there is a common joke, but there's some truth in it too. If you work with sensitive information, you have to keep some of it secret. So I guess in Turkey, this is done in Gebze. TÜBİTAK has an institute there. Because every country has to do it themselves, right? You can't just buy it. If you buy it, but there are papers who tells you what are the common techniques of building these mathematical locks, but the common techniques depends on parameters. That as a country, you can change those parameters. Like if there are 10 different techniques, you can use technique 3, 5, 4, mix them together in some sequence. And then you build your lock, you build your cipher using these techniques. It turns out that every country is doing this, a combination of these ciphering methods. What happens is, sometimes you build these locks, and it turns out to be very easy to break. You cannot control how difficult they become and how secure they are. So you hire people in your institute, try to break them. So there are code breakers in your institute as well as code makers. So these people who are trying to break them also uses mathematical papers, which gives you common ways to break these codes. So they try these techniques, and if the code survives all these things, they get a security number. So like most secure ones is, say, secure out of 10 out of 10. Less secure ones get 7, 5, 4. So when you build this code in random way, using these techniques, say you build 100 of them, chances that only like 10% is very secure. The rest is less secure. So your country uses them depending on the security levels. So if you want to pass a very, very sensitive information, you use the very good codes, but then you use them, they're gone, so that you shouldn't use only those good ones. So use the less good ones for less important information. So this is how it goes. Apparently, there are people who work in Gebze to break these codes, and then they give a number to these, how secure they are. And how do I know this? I had a student who worked there for a while, and he did this one, he told me. So this is what we are doing, he said. And he took, mathematics courses, and then graduated, and he went and he did this. So, sorry. Okay. Any questions? Anything else? Yeah. Okay. We spent more time on this than I expected. So. Okay. Let's finish in a lighter mood. Let's say you have a homework. This is second homework. Do Tuesday. This time I'm giving them from Grimaldi. So Grimaldi is this book, and the one it's in the bookstore is also identical, just the cover is different. And these are around page 240 to 230. So this is from our textbook. So it's 240, 240, and so on. I guess this is 220, 230. So you can easily find them in the pages here. Exercise at the end of 4.3. Okay. By the way, I said too many things already, but recently there were some articles in newspapers mentioning a Turkish mathematician getting some big award, proving something very important in number theory. Any of you read any articles on this? So this news was about Yalçın Yıldırım. He's actually was in Bilkent before 2000, I guess. Now he's in Boğaziçi. He proved something that led the way for better results about prime numbers. It's related to something called twin prime conjecture. So let me say a few words about this before we move on to one more thing. We just saw there are infinitely many prime numbers, right? There are infinitely many prime numbers. So they're randomly in number. You can actually prove that there are as many big gaps as you want between primes. So you can make the prime, you can find two spots in the number scale where there are no primes for as long as you want. So you say any number you choose, 100, there's a spot in the number scale that there are no primes for 100 numbers. So it can be as large gaps as you want. But at the same time, there are certain primes that seem to be only differ by 2. There are quite a few of them. At the beginning, you see quite a few of them, 11 and 13. 17 and 19. But of course, 19 and 23 difference is 4, so they're not that. So a pair of primes is called twin prime. If the difference is 2. Okay? So there are some twin primes, which very interesting phenomena. We observe that there are these primes, even big primes that differ by 2. And the same question we ask for just for primes, you can ask for them. Are there infinitely many twin primes or not? And that question is open. So it's like if you solve it, next day we'll take you for the limousine and you're famous. So it's one of the most open and interesting problems. Are there infinitely many primes? Huh? Maybe tonight you'll come up with an argument similar to the other proof we had. You can prove this.
Mathematical induction.
Maybe induction. But believe me, I mean, you'll get so famous that you wouldn't even want that kind of fame. It's a hard problem. I mean, it's very hard. But I mean, we were like thinking that it's unreachable and so on. But recently, it has been proved actually. You can find infinite many primes whose difference is smaller than 5,600 something. So there is a number now where you can find 2 primes whose difference is less than that number. It's actually first announced that there is a number like 4 million or something that you can find infinitely primes with differ less than 4 million. And that guy became famous. It's on newspapers everywhere. And then a group of people dropped it from 4 million to something small. Currently, it's like about 5,680. But you can find infinitely many primes less than some number difference. That's proved. And that 5,000, people are working to make it smaller. What Yeltsin did is, he actually got the award for this. So it's a very, very important result. He started this, basically. This, you can find a finite number that there are infinitely many primes less than that, whose difference is less than that number. And he, I mean, for mathematics, very important, he got something called Cole Prize. Cole Prize. And he got invited somewhere and so on. So it's a very big deal. I mean, I think it's one of the biggest things number theories received in Turkey. So it's important.
Why is this so hard to prove?
Why it's so hard to prove? Because primes are very chaotic. I mean, to understand, there is no regularity how the primes are distributed.
We don't know the pattern.
Yeah, there is no pattern.
We also don't know where to look at, right?
Mm-hmm.
Is there any clustering or something?
Yeah, the difficulty is they just spot out randomly in number plane. So you're trying to understand, like, I mean, there are some patterns. Some number theories found some relations between, like, how many primes you can find less than a number n. There's an estimate for it. Less than a number n, how many primes there exist? It's n over log n or so. So there are estimates like that, you can say. There's also well understood, more complicated mathematics that related to prime numbers. Let me write a question and then we'll finish with this. We have 5 minutes, so I'm not going to. But some of you may wonder, so there are these 9 numbers, 2, 3, 4, 7, 10, 11, 12, 13, 15. And I have a 3 by 4 square where I have 8 spots left. I want to put these 8 of these 9 numbers in here so that the sums are always equal. These sums. And these sums are also equal. So when you sum up the rows, you get always the same number. If you sum up the columns, you always get the same number. Out of these 9 numbers, 8 of them goes to boxes. Which number doesn't go to the boxes? This was a final exam question last year. So this is the kind of questions you should expect in number theory. This is a number theory question. It's not a Sudoku question or a puzzle question. You have to use number theory. I actually mentioned that too. Which of the 9 numbers cannot be justified? Justify your answer using number theory. So you have to argue also why that number has to be left out. Okay? Think about this. I mean, this is something I want to give you a sense of exams a little bit. what kind of questions you should expect in exams. Like this is one of the questions, for example, that number theory is used to identify the number which is not, it can't go into. Anyway, this is a cute question. I thought you may want to enjoy. Anyway, think about this, but don't forget your homework, which is for Tuesday. So the homework assignment, again, do in such a way that you're not going to write the answers or bring your papers, or I'm not going to collect it. I'll give you a quiz problem from one of the questions, and that's how we do it, okay? All for today. And